Uh, Welcome back, class, for the lecture on the local search for optimization problems. This over here it is the chapter that is taken from the book Artificial Intelligence: A Modern Approach, and it is the chapter number 4 in that book. So in this chapter we discuss some of the local methods, some of the methods for searching locally in a region, and the goal is to optimize optimize the solution. We are not interested to find the best possible, but we have some criteria and we want to uh, get the best from the given situation. We want to get the objective function satisfied. So we already know the different types of searching techniques out there. Some of them are dealing with systematically explore all the possible situations. Complete search space, we try to explore it, which will take too much time. Why these methods of local search are used? They are used because of the reason that uh, the in the practical world the search spaces are extremely large. The problems, they can be very large, and we cannot solve them using even very high speed supercomputers. We cannot solve them in some reasonable amount of time. So just imagine if you are given a very small amount of time and you are asked that in the world there are maybe many million cities, and I ask you to find out the best possible city amongst the cities in the world related to the temperature. So there are so many cities. You cannot go through all those cities in one day maybe. So that is the thing that we cannot explore in the traditional approaches in optimization or in artificial intelligence. The goal is to to explore the full search space possibly, and sometimes you have some sort of help. For example, the case I gave you, the case study I gave you, that in the whole world you want to search the city that has the ideal temperature of 25 degrees Celsius. So for 25 degree centigrade temperature, you already have a little bit of idea that you will not be searching such a city on the North Pole or on the South Pole. Okay? So little bit of helping will allow you to prune the answers, to cut some of the options. You don't want to search North Pole or South Pole. Similarly, you will not be searching those countries, a lot of countries that are very cold or very hot. For example, countries in the upper part of the Europe, you will not be finding the ideal temperature of 25 degrees centigrade over there. Similarly, many countries in the Middle East, they don't have 25 degrees whole year. They don't have 25 degrees Celsius temperature. So that's why always you will have some sort of help. But still, practically there are many problems that cannot be solved with such techniques. So just to give you an idea, some of the search problems, they have normally 10 to the power 100 states, and it's very common, a very normal average amount of space or options that you have to search. And maybe you have heard about the computer programs that are playing chess games, the game of the shatranj, or there are some other computers now, they are playing the game of Chinese game of Go, or there are many other games that computers try to play. These games, they have big search space. The number of possibilities that the player can take, they are a lot. So sometimes they are up to 10 to the power 30,000 states that are possible for such real world problems. Clear? So that is the reason. So if these are the problems are smaller, like business problems, how to optimize something, that is a smaller issue. But in many cases, the problem space is so big, we cannot solve it with simple regular technique of searching all the possible situations. It is not possible. So for this we need a completely different approach, and such different approach there can be two. One is to search locally in some area. That's what we will cover over here in this chapter. Or there are some techniques which are called iterative improvement methods, which where we try to improve repeatedly. Iterative means repeatedly, and these are the topics for the advanced part of the courses. So we will be considering some of the examples where these things can be used. So always when we want to seek a goal state, we want to know what is the goal, but we don't care how we reach over there, that goal. These are some of the examples we will consider over here in this case. So n queens is a problem. There is another problem of map coloring, and then there are problems, very famous problem in computer science called traveling salesman problem. We will discuss these. The others we will not be discussing here. And by all these problems, the common thing in these problems is that they focus on the goal state. They are not interested in how you reach the goal. They are not like in the case of a Google map. You want you want to go from Buremi to Muscat. You have to keep track of all the cities that you pass through. But that is not the case in these problems, where you are only interested in the final solution. So what is the key idea for local search methods? So remember, local search method, it is a type of method where you try to find out the best possible solution for a very large search space. So the key idea is extremely very simple for this approach. What you do is that, for example, these dots over here, these green and yellow dots, this represent the different types, different possible states or conditions of a system. So there can be millions of such different possible states, and you want to select the best one that represents your problem or your objective function. So in this case, what we do is we randomly, now the word random is important, you randomly select the initial state. So out of maybe million or more states, you randomly select one of them, and then what you do is that from this random state there are many of its neighbors. So let's say let me change the color. So let's say there are many neighbors for this random state. What you do is that you select only that state which is improving. So for example, for this random state, your cost or your objective function value, maybe it is 4. Okay, and you want to maximize over here. So what happens, you want to maximize the profit or something, and you check out all the other states, and you find that this state, it has got maximum advantage, that is 6 for this state. So you transition from the starting state to this one, and you then keep on doing this from the surroundings. You do it randomly, you make local modifications to improve the current state, and always you evaluate the current state and move to the other states. So evaluation or testing is continuously you are doing it, and you keep on improving on the starting point. And then you keep repeating this loop until you are satisfied, you reach some goal, or you reach a point where you think now it is enough. This thing is and the profit or the objective function value, it is as per my requirements or goals. Clear? Pause it. If it is not clear, take a time, take a minute, absorb this information, then we go next. At any step, if you have any questions, come in the group and we will discuss over there. Ask questions. So I will give you some examples. One of the examples that is very common, very popular, most of the people in computer science or related areas, they know it. It's called the traveling salesman problem. This is a huge problem. Uh, uh, Still it's not 100% solved. Scientists are always thinking and working on this problem. So it is called traveling salesman problem. And here on the screen you see the map of France. You see almost all the major cities of France. And what we want to do is that we want to there is a salesperson. For example, he works in some company and he has to deliver the sales items. For example, he works in beverage company Coca-Cola, and he has to deliver the products in every city on the map. Okay, and for example, there are 30 or 40 cities. He has to go to all the cities and he has to pass on the items and then go to the next city. So for this purpose, definitely one important thing is that he has to go to each city only one time to save the fuel costs. You don't want to go to one city multiple times. He has to go over there. That's not good. So he wants to go to a city only one time. Do is that repetition is not allowed. And the second important thing is that when the salesperson is traveling, he has he wants to cover the minimum distance. That is the objective, that's the goal. Okay, so minimum distance, how it will be traveled when he is traveling with the minimum distance near the surroundings. Okay, now for example, if he is trying to go from the city of Paris to the south in the city of Toulouse, this one, that's a very bad option. Very bad option. It's taking too much time only to reach a far away city. The best option is to go through the nearer neighbors and then keep on moving to the south one by one. So now this problem is not so simple. This problem is one of the problems that are called as million dollar questions. So I don't know, I think it was in 1970. There are 7 or 8 questions that were posed by some organization, and they said that these are the challenges for this century and the next century which are not solved, and anyone who can contribute, any scientist who can solve it, they will get $1 million reward for that contribution. So out of those 8 challenges, only I think recently there was one problem that was solved by a Russian mathematician. All other problems are still not solved. One of them is this one that you see over here. So what happens is that you have got this set of cities. You want to find out the best route that minimizes the fuel or petrol consumption. So one method is you do the exhaustive search. You take all the cities, 30 or 40, and you try all the possible combinations and try to find the best possible solution that has minimum distance. But do you know what will happen? This is practically impossible. This type of problems, we call it, in terms of algorithm, it has factorial time complexity. It will take this much time, n minus 1 factorial divided by 2. So those of you, if you remember what is factorial, so factorial of, for example, 3 is 3 multiplied by 2 multiplied by 1. But as the numbers grow, the factorial grows very, very quickly. So if there are 36 cities on this map, you will have to search this many different possible solutions. So this is huge. This is not possible for even a supercomputer to solve all these solutions, maybe even in 100 years. It's not a viable approach. It's not possible. So practically these are some of the problems that are not possible to solve via normal approaches. You can't find the best possible solution for this because there are too many states. You cannot search them all one by one. So what to do? One possible solution in the local search method, if you go back, what I said over there, what is local search? Local search key idea is select a random initial state, and then number 2, make local modifications to improve, and number 3, repeat. So what we do is over here, take a start from an initial solution and you try to improve using local transformations. So initial solution, this is one solution given to you. So just select this one randomly, and this selects all the cities only one time, and it seems reasonable. There is no such thing over here that you can say that it's taking too much distance. Now how to make the improvements, how it can be done? So improvement can be done in this case. Let's say, for example, you have got over here 4 cities A, B, and C, D. Okay. So there is a connection between the cities A and B. Okay. And then there is a connection between the cities D, C, and D. Now what happens is that you can see over here that this is a huge distance between AB and CD. What you do is that from this whole map you disconnect 2 of the paths, or 2 of the wires, you can say 2 of the strings, you disconnect them. Okay, so when you break those connections, then you reconnect them with the different poles. Okay, now with the different poles means that when A was connected before to B, now the A must be connected to C. Okay, it cannot be connected to D. Why? We cannot connect A and D because it will make 2 smaller subgraphs, which is not feasible. They are not connected. Remember, one of the purpose is that the whole cities, all of them, they should be connected. If you are trying to connect C, A and D, that's a bad option. It will make problem. Okay. So this is it. If you have only one option left, which is A and C, so you connect A and C, then the remaining one is B and D. Now to find out if there is any improvement to the local solution, to the initial solution. How to find out this improvement? This improvement you can find out by measuring the distance AB plus CD. So AB plus CD, is it smaller than AC plus BD? If that question, the answer is yes or no, that is important. So AB plus CD is one option, and the other option is AC plus BD. Okay, sorry for the drawing. So what happens here? You will select the new state and the new solution AC plus BD only if its distance is lesser than AB plus CD. So if this AC plus BD is coming out lesser, that means that your new solution, this one, it is taking a little bit of less distance than the original one. Clear? That is the purpose over here. That's what is happening. So pause it, go through it, think over it, and again ask questions, whatever you have got. So remember, in this case over here we are trying to optimize the distance. So the distance is given over here. The Z optimal, for example, is 4,441 kilometers. So you always try to make this distance smaller. In this case, this is like a minimization problem. Clear? So this was a two swap solution. What you do over here is you do two mutations or two changes. So you choose two edges at random, whichever you think maybe they are very very long. So you take them randomly, and what you do is you remove them and then you reconnect them in the different way, and there is only one valid new way that you should remember. I told you in the last slide, if you disconnect A and C, no, disconnect A and B, then the only option left to reconnect them is A and C. That is the only possibility. So like this we do over here. We reconnect them in a different way, and we focus on if it's improving. Remember, the point over here is if there is no improvement, you will discard or ignore this solution. You will keep on trying until you find something that is better than the current solution. Okay? So this was the first problem, traveling salesman problem. Let's move to another one. It is called the N queens problem. Now the N queen problem is simple. The problem states that, let's say, all of you, maybe you know what is the game of chess, shatranj, or if you don't know, just Google it quickly. The game of the chess, normally it is played on a checkerboard. So it's a board that has boxes with opposite colors alternating. So there is white box, black box, white box, black box, so on. Normally the chess board has the size of 8 by 8. Okay, and in the chessboard there are many different types of pieces or elements. Here in the N queen problem, so this problem is not so important. It's not a real world problem. Remember one important thing: the previous problem, traveling salesman problem, it's a very serious issue. It's very important problem. Once a long time ago, I saw a job posting somewhere, I think in Dubai, that was related to, I think, these taxi services, I think, Uber or Kareem. And in their job requirements, they wanted a person that can work on, that knows, that has the understanding of traveling salesman problem, because their algorithms, they want to, for example, a person asks for a Uber or Cream ride, so they want to route the nearest taxi to that person. The nearest taxi that should come to that person. That's the priority of their algorithm. So the important point I want to say is traveling salesman is a serious and important problem for the businesses, and it's something that is still evolving. There is no final solution to this problem till now. But N Queen, it's just a small trivial problem, not important. It's like a game. So here the normal chess boards, they have the size of 8 by 8. There are many different types of pieces, but over here in this game we consider a small version of the chess board. For example, this board over here, it has 4 by 4 pieces. Okay, so total there are 16 boxes, and in this box we want to put 4 queens. So if the box size is 4 by 4, then we put 4 queens. If the box size is 5 by 5, then we will put 5 queens. So what is a queen? queen is a player in the chess game that can move. So for example, if this is the queen, queen can move horizontally x-axis. It can move any number of positions in y-axis, and it can also move anywhere in diagonally. So practically saying, queen is a very powerful component in the chess game. It can move in a straight line in any direction but in a straight line, and it can move up to any number of positions. So it can move whatever positions over here. On this side it has got two positions available, it can move there, any two of them. Below it can move three positions, 1 2 3, anywhere. Okay, but it cannot move other than the straight line. So for example, this queen is not attacking this piece. Okay, so what this game says over here is that you have to place 4 queens on the chessboard such that they don't attack each other. So normally, remember, if you have 4 queens, you will be putting 1 queen in each column. Okay, if one column has 2 queens, definitely they are attacking each other. So practically you will put 1 queen in each column, and you want to minimize the number of attacks, and ideally there should be 0 attacks. So the evaluation in this case, so the states over here, in this case you have 4 queens in 4 columns. That's your starting. Operators or actions, what you can do is you can move the queen in the column. So for example, you put a queen here, you can move it up or down. Clear? And goal test in this case over here, what you want to do, what is your objective function, is that no queen is attacking each other. And how you evaluate it, how you test it, the evaluation criteria is represented by H, and it says that the number of attacks, they should be 0, no attacks. So in this case, if you see the first option, so there are 4 queens, and if you see these lines, they represent the attacks, and there are a total of 5 attacks. So the H value is equal to 5. This is the random solution you selected. So this is your starting point, which is random. You selected it, and it's a bad solution. Okay, now what we do, remember the 3 steps. Start random initial solution. Then what you do is you move a little bit around the starting point. You make a little bit changes from this random initial state. So what little bit change means? You take one piece, for example, from here, and you move it, for example, up. You move it up. So let me put a red color here. You move it up. Okay. Now when you move it up, you can move it in other directions also. So you take one column only one of the queens, and you move it up or down. And when you move it, you try to check if the score is decreasing. Yes, it is decreasing. Before it was 5, and now it has become 2. Okay, and you keep on doing this, and then you go, now this becomes your initial state. And then so once you decrease the H value, you just forget the past solution. You don't memorize, or you don't keep track in the memory of the past. You do this, and then you move next, and then you play with another one. So this time you move one of the queen from here to this place, and in this case you see that H is becoming 0. Now one important question, what if and the number of queen attacks are not decreasing? Yes, it is possible, 100%, that sometimes it will happen that your solution is in such a state that you cannot improve it. So there is no guarantee in local search methods that you get a solution or you get an optimization. So there is no guarantee. But still these methods are used. Remember, these methods are the ones that are practically used in the industry, like the traveling salesman problem you have seen. And what you do is that you prefer these methods because they still work on very, very large search spaces where you have millions of possible states. Clear? So think over it, pause the video, and if you have questions, ask. Next problem that comes is related to the graph coloring. So all these problems I am giving you, and then we will discuss the algorithms, how to solve them. So one of the algorithms we have seen is for local search. We will see some others also. First we go through the examples. Graph coloring is a very important example. So this one is also not trivial, not it is very, very important, this one, and I will give you a brief history from the past. In the old times, this problem is not for the current times. It is in the old times, almost you can say more than 100 and 150 years ago, when the printing press was created newly. Okay, so in the industrial age, the printing started in the big factories. For example, to print the books, to print the big maps. So in that case, at that time, there was a big problem. There were not simple printers. There was a very, very big setup, and if you wanted to print colors, you, for example, will take the blue color, and on the map, all the places where you have to paint the blue, you will paint it on every place on the map. Then you have to go and clean the box, and then you put another color, for example red, and this time wherever on the map there is red color to be used, you will put the red color. Okay, so for example, this is a map. So there is one country over here, any country, country number 1 and 2 and 3 and 4. So this is first one. Okay, so what is the purpose over here? These are the different countries shown. Now the important thing was at that time, especially for the maps, that you wanted to show the neighboring countries in different colors. So for example, this country number 1 is Oman, and the country number 4 is Arab Emirat, UAE, and you don't want to show them near to each other in the same color. So for example, 1 is in red color and 4 is in red color. It's not a good option. Why? Because if they are in the same colors, it is not easy to see the boundary line, the border between the two countries. And one of the important purposes of the maps is to identify the different regions clearly. So that was the problem at that time, that you don't have the chance of mistake. You don't have computers. Think about a time 150 years ago. There were no computers. There were no computing machines at that time. So what they wanted to do was, they had some regions defined on the map, and they want to color them such that no two neighbors had the same color. So this thing was called as graph coloring problem. And this graph coloring problem, like traveling salesman, it can have many solutions depending on the number of different regions or countries. So if you have 20 or 30 countries, then this problem is a huge issue. It's not so simple. So how we do this? We solve it again just like we did for traveling salesman problem or the N queen problem. This problem is also solved using the local search method. First of all, what you do is that you select one color scheme randomly. The word important is random. So you randomly select the different. So here you see the names of the different boxes are given as ABC. So they are given here in capital. So for example, A, B, C, D until F, and you put over here these small letters for the different colors. So small b is blue, then G is green, R is red. Okay. Whereas there is another color given over here, capital B, it is I think brown. So small b is blue and capital B is brown. So they are not same. And then there is a capital R. Small r is the red color, but the capital R is, I don't know which color is this. So just imagine any other color starting with R. So what they do is that they started the first iteration, the initial solution. In this case, they put the colors over here. So let me try this. I have to, okay, I erase it all. Now, their initial solution, they says that A has the color B. So A has the color B, blue. Whereas the B and C, so this is B, has green and green. So, and then the D has got the red, R has got the blue, and F has got the red again. So this is the initial scheme of colors on the map, and the problem is you want to make sure that the neighboring boxes should not have the same color. So that is represented by the conflict. So how many conflicts are over here? Just pause it and think over it. What you think? What are the different conflicts? So in this case, and the conflict here you can see clearly the two neighbors A and E, they have the same blue color, which is not good. And then there is another conflict over here, the D and F, they have the same color R, red. Okay, so we want to reduce this, and what we do is that from our initial solution or initial starting point, we make a local modification. So that's why we call it local search method. We try to search the solution by making local changes. So we do a local modification, and in this case if you see, the modification is this one. In the state D, so D is, where is D? D is this one. So in the state D, what they do is that instead of R, they put over here the color brown. Okay, so with the brown color, they have reduced the conflict. So this color is not now equal. We have reduced the conflict, and number of conflicts now are 1. Okay. Now there is another problem. Remember, you have introduced one extra color. Remember, in the old times, changing colors or putting more and more colors was more costly. You have to do this with minimum number of colors. Definitely, if you have 6 boxes and you give every one of them a different color, then there is no problem. 6 boxes, 6 colors, there is no conflict. But practically, in the old time, colors were not so easily available to use, and always you wanted to use minimum number of colors so that you don't have to fill the boxes, color box in the factory again and again. So here they have used brown, a new color, which is not good. And later on what you do is they make another change, remove this blue, this brown, sorry, and change it with the blue color instead of red. Now from red it became brown, now it is blue. And then you go to the A, so A is this one, and for A what you do is you change the blue color with the capital R color, and in this case you will see that now they are not equal. There is no conflict in the whole map. You don't have any conflict now. And we did it in 2 or 3 steps, but maybe practically you will repeat, or you will go through 10 steps, 15, 20. There is no guarantee. Remember, in this type of approaches, there is only trying again and again, and there is only luck. There is no guarantee for the best answer or for the best time. So go through this example. If you have any questions, ask, then we proceed. Okay, the next, there is a small problem given set. We will not go here. This is related to the Boolean algebra that you study in the digital logic design. Same Boolean algebra, they discuss it over here, but we will not discuss over here for us. So leave it. So in general, what is local search? More formally, the search algorithms we have seen till now, so far they keep track of the current state, and what they do is that they fringe off the search space and the path of the final state. So what we did in this method till now was, you select a starting point and then you take a little bit of changes, and you try to search in the neighbors of the current state, and you try to find the final state. In some problems, we don't care about the path to the solution. So if you are using Google Maps, you want to go from Buremi to Muscat, it is very important. That is also an optimization problem, because remember, when you want to go from Buremi to Muscat, you don't want to go from a very long path which may take 2000 kilometers. It's not feasible, not good. So that is also an optimization issue, and you want to go from Buremi to Muscat with the minimum distance. So but in that problem, the important thing is that you are interested in the whole path. You want to know which are the exact number of cities that come when you go from Buremi to Muscat. So you will go from here to Wadi Jizi, then to Sohar, then to other cities, and then to Muscat. So that was one type of problem where you try to find the current state and you go through the search space by following a path to the final state. But in some other types of problems, which we normally call as optimization problems, where we are not interested in the solution path. Okay. So in that case, for example, the example is 8 queen. You are not interested that how you find the minimum number of queens attacking each other. 8 queen means 8 queens on the board of 8 by 8 size. So in that case, you use the local search algorithms that operate on a single state or a current state. So at a time, you have only one state that you change, and you try to find the best possibility. And what you do is you move to one of the neighboring states, and you don't record or maintain the solution path. That's why we call it local search. You find the answer in the locality. Clear? So this was the example. You start with the initial state, this one. This is your initial state. You try to improve it, make a little bit of changes, and these changes are done through local transformation, means only small change to the initial solution. That's why we call it local search. And finally, you try to reach a solution that is the best one. That's the best possible solution. Clear? So in all the local search algorithms, the basic idea is that local search algorithm, it operates on a single state. At one time, you are only keeping track of only one solution, one current state. You keep track of it, and you try to move to one of its neighboring states, neighboring solutions. And the principle is you keep a single current state and you try to improve it. Improvement is the important keyword. So you don't keep track of the path, and that's why we call it local search. What is the advantage of this approach? You don't need to keep you don't need to have a very large computer or system memory to process such problems, because at one time you are only dealing with the one or two maybe so current states. So for example, if you remember, if the h value of this second problem it is less, for example it is 2, you will remove the last one which has 5. You just discard it. You don't keep it in memory. When you are improving, you remove the past solution. You don't keep it in memory. That's why it uses very little memory. And this type of approach, it is more applicable in searching when you have a very large or sometimes almost infinite search space. These types of solutions or algorithms, local search algorithms, they give you a reasonable solution in such infinite or large search space problems. Clear? Some more properties of local search. Local search algorithms are very useful for the types of problems which we call as optimization problems, where you want to optimize or find the best solution, or you want to you have an objective function, you have some criteria or objective function that you want to improve. And such problems, the problem space or problem area is so large that you cannot systematically search the whole area, the whole set of options. So what we do is that we start with a suboptimal solution. Suboptimal means that not so good. So you start with a suboptimal or not so good solution and you try to improve it. And what is the goal over here in this case in local search? You try to find a state such that the objective function is optimized. Okay. In the case of chess game, n queens game, you want to minimize the number of attacks. So it depends on your criteria. Sometimes maybe someone says that my goal is there should be no attack, h is 0. But maybe in some other cases someone says I don't have time. I want to solve it very quickly, and any solution, any number of attacks less than or equal to 2, that is enough for me. So it depends on the criteria of the person. Clear? So here is the summary for the local search, how it works. So this is an example of the search space landscape. So this thing we have seen many times. For example, here you see on the x-axis you see the state space. These are the different possibilities of the states. And on the y-axis you see the objective value, for example the cost or the profit. So for example, if it is the profit, you want to maximize. Okay. Or if it is the cost, you want to minimize. Okay. So if it is the profit, for example, your ideal is that you want to get this value. So you want to get this state or this condition or this hala which gives you the best value of the objective function, the best profit, for example. Some other issues related to this type of landscape is that the states, they will give you different types of values of objective function. Okay. So sometimes they will give a very high value. Sometimes it will give a very low value of the objective function. And because you cannot see all of them because they are so many, remember, important point over here is that the state space, maybe it has got 10 to the power 20 states, millions or billions of states. You cannot see all of them. That's the important point. So in this case, what you want to do is that you start randomly, for example here. So when you start randomly, you try to improve. Okay, you will not select a state that is making the profit less. You will only select the options that will make the profit more. Go up and up and up until you reach some point. Now here are some of the important definitions that are important to you should know, and that are also important for your exams. One is called as local maximum. Local maximum means that this value over here that has reached, it is the maximum in this region. Okay, when you reach here, you cannot go any further anywhere else. But maybe out of all those millions or billions of states, this is not the best. The best value is maybe this one. Okay, this is the best, this is good, but it is not the best. The best value is this one. Okay, so the maximum value in some locality, we call it local maximum, but the overall maximum out of all the state space, we call it global maximum. And one important point is that global maximum, you cannot be sure that a state space has a global maximum value. You cannot find it out unless you have explored all the possible states. Clear? Now there is another thing that occurs sometimes. Sometimes inside the states you will reach some point like this one. So you can give it many names. There are many names given for this thing. It is maybe called as shoulder, or sometimes it is called as saddle point. Saddle means the seat that you see on the back of the horse. So if you see on the back of the horse, the seat is something like this. Okay, so it has starting below seat, and a person sits here. This is the plain area, and then it goes up. So this is also like that thing. So there is a low point, then there is a smooth, and then there it goes high again. So you can call it like a shoulder. Maybe this is your these are the arms. This is shoulder, plain area, and then this is the neck and head. So in this area over here, this is not your best. You can still improve, but if you keep on searching in a very small area, maybe you will think that there is no improvement. If you only go for 3, 4, 5, 6 neighboring states, maybe you don't find the best solution. So what to do? How to do it? So for example, you start randomly over here, and then you try 2 or 3 times, and then you say, no, finish. I could not find. This is the best. This is local maximum. But practically it's not the local maximum. Okay. So there are two types. One is called a shoulder or saddle point. There is another one over here. This one. It is called flat local maximum. Flat local maximum, what it means is that the values, the profit value for all these points on the top, that is same, the objective value, function value. So it is like the local maximum. You cannot improve it further, but all of them are possible solutions. There is no one solution for this problem. So maybe there are 10 points over here, 10 states, all those 10 states. So here it is. All those 10 states in this region, they will have the same profit value. Clear? Now with this background, we have seen from the start of the chapter what we saw. We saw the local search method. Then we saw the 3 examples: traveling salesman problem, n queens problem, and the graph coloring problem. And then finally you see over here this state space landscape, the overall map of the state space. And you see the problem over here is that there can be many different types of high and low values. So if you want to maximize, your objective function is to maximize something, you will also see the local maximum, you will see the flat local maximum, or you will see the saddle point or the shoulder, and then there is the global maximum. That is the ideal for your problem. So with this given criteria, how to solve a problem, that's a big issue. For this comes the next of the topics, local search algorithms in detail. So I think we should take a little bit of break and then we can continue with this. So yes, we should take a little bit of break.